Okay, welcome to the deep dive. Today, we're actually turning our focus inwards, looking at our own cosmic backyard, you could say. We're tackling a really fundamental question, and one that's surprisingly tricky. What's the real story with the spiral arms of our Milky Way galaxy?
It really is fascinating, isn't it? I mean, the challenge is huge. How do you map out the structure, those arms especially, when you're stuck right inside it? It's like trying to draw a map of London while sitting in a cafe in Soho.
Exactly. So, you've brought together some excellent sources on this, covering, well, everything from the basics to the absolute cutting edge. Our goal here is to unpack all that material and see what scientists are figuring out, and maybe more importantly, what they're still debating about these arms.
Yeah, well, look at how they even try to map them, from our perspective.
Right, and then get into the different ideas about how they form, how they evolve over time.
And definitely the impact of new data,
Mhm.
especially from Gaia. That mission has been a game changer.
Absolutely. But as you hinted, the sources suggest that even though it's our home galaxy, the
Huh.
picture is, well, it's messy. Still a lot of uncertainty.
Prepare for some complexity. It's not as neat as the pictures might suggest.
Okay, let's start with the fundamentals then, based on these sources. What's the basic picture of the Milky Way?
Well, the consensus view from the material we have is that we're in a barred spiral galaxy. So picture a central bar-like structure and then arms swirling outwards from that.
And it's big, right?
Oh, huge. Roughly 30 kiloparsecs across. That's about 100,000 light years, give or take. But the main disk, where we are, is surprisingly thin, maybe 220 to 450 parsecs thick. So let's say 700 to 1,500 light years thick compared to 100,000 light years wide.
Wow, like a cosmic frisbee. And where are we in this frisbee?
We're out in the disk, yeah. About 8.3 kiloparsecs from the very center. So not downtown, more like the suburbs.
And the spiral arms themselves, what are they fundamentally?
They're basically regions further out than that central bar where things are denser, more
Hmm.
gas, more dust, and crucially, that's where most of the new stars are forming. They're the bright bits you see in photos of other galaxies because of all those young, hot stars.
Okay. And the sources list the commonly cited main arms: Perseus, Norma, Scutum Centaurus, and Carina Sagittarius.
That's right. Those are often considered the big four. But there are also smaller features, spurs or arm segments, like the one we're actually in the Orion Cygnus arm, or sometimes just the local arm.
But you mentioned complexity earlier. Is it as simple as just four arms plus some spurs?
No, not really. That's where it starts getting debated. The sources point out there isn't total agreement. Some ways of looking, maybe tracing older, redder stars, seem to show just two main arms dominating.
Two. Okay.
But if you look at the gas clouds or those young blue stars,
Hmm.
that evidence points more towards four arms.
So different tracers give different pictures.
Exactly. And it might be even more complex. Some research suggests there could be like two separate spiral patterns overlaid on each other, maybe an inner pattern and a different outer pattern, perhaps rotating at different speeds.
Right, because these arms aren't solid things. They're more like patterns, maybe traffic jams. And the sources stress they aren't neat spirals either. They branch, they merge, they get twisted.
Absolutely. They're dynamic and messy. And trying to map that mess from the inside, well, that's why there's still so much uncertainty about the fine details.
So how do scientists try to map them? What techniques are mentioned?
There's a whole toolkit. The sources list things like observing hydrogen gas HI regions using radio telescopes,
Hmm.
looking for masers, which are like natural microwave lasers from water molecules in star-forming regions,
Okay.
mapping molecular clouds using carbon monoxide signals, finding pulsars near HII regions, using infrared surveys like 2MAS and Spitzer to see through the dust and map out populations like red clump stars, or mapping clusters of stars with Ys. Each method gives you a different piece of the puzzle.
So you're essentially trying to connect the dots using these different tracers, hoping they outline the same structures.
Pretty much.
Hmm.
But sometimes the dots don't line up perfectly, which leads back to the different interpretations. Two arms, four arms, branching arms.
And beyond just mapping them, understanding why they exist is a whole other challenge, isn't it? The sources say there's no single agreed upon theory for their origin and evolution.
Correct. Big area of debate. One major idea is that they kind of arise naturally from the disk itself. It's driven by the gravity and motion of everything in the disk: stars, gas, dark matter.
The self-generated, you mean?
Sort of, yeah. The Selwood and Masters review mentions models based on self-excited disk instabilities. There's this concept called groove modes mentioned.
Groove modes. Sounds musical.
Huh, maybe a bit. The basic idea, as the material describes it, is like an internal feedback loop. If you get a region with slightly less angular momentum, it can trigger an instability. This grows and creates features, grooves at specific places in the disk related to orbital resonances, the Lindblad resonances.
Mm.
And this process can kind of feed itself, potentially creating and maintaining spiral patterns just from the internal physics of the disk, like the disk is constantly stirring itself up into these patterns.
Interesting. So internal churning creates arms. What's another possibility?
Well, there's the classic quasi-steady density wave theory. This has been around a while.
Yeah,
The idea here is that the arms aren't just temporary clumps, but a more stable, long-lasting pattern, a wave of higher density moving through the disk.
like that traffic jam analogy.
Exactly. Stars and gas clouds approach the arm, slow down, bunch up, making the arm dense and triggering star formation, and then they move on through.
Yeah.
The pattern itself persists for a long time, even though the individual stars and gas aren't stuck in it forever.
Okay, so internal instability versus a more stable wave pattern. But the sources also bring up an external factor, something about a collision.
Yes, the Sagittarius dwarf galaxy. It's a smaller galaxy that's currently merging with, or being torn apart by, the Milky Way. There's a strong suggestion that interactions, like past close passes of Sagittarius, could have actually triggered or significantly shaped our spiral arms.
So an external kickstart.
Potentially,
Yeah.
or at least a major influence. And one key way scientists try to tell these theories apart, internal, density wave, external trigger, is by looking very closely at how things are moving.
The kinematics.
Precisely. They look for specific patterns in the velocities of stars and gas, these large-scale streaming motions, and compare what they observe to what each theory predicts.
And this is where Gaia comes in, big time.
Absolutely. Gaia has just revolutionized our ability to measure those motions for billions of stars. Its whole purpose, really, or a major part of it, was to get super precise distances and 3D velocities to map out the Milky Way structure and dynamics, including the arms.
Let's walk through what the different Gaia data releases have revealed, according to the sources. What about the early stuff like DR1?
Even with Gaia DR1, which was kind of a first taste, studies started looking. One mentioned used about 77 Cepheid variable stars. These are useful standard candles near the Perseus arm.
What did they find?
They found correlations between the stars' velocities and how far they were from the arm center. And based on simulations trying to match these observations, the results actually lean towards a model where the Perseus arm is maybe a transient feature.
Transient, meaning not permanent.
Yeah, maybe something temporary, perhaps even in the process of breaking up or dissolving. So that early result challenged the idea of stable, long-lived density waves, at least for that arm.
Wow, okay. Then came DR2. That was a huge step up, right?
Massive. Millions of stars with the full 6D data position and velocity and good accuracy. The study by Katz and collaborators used like 3.2 million giant stars to map the velocity field way out into the disk.
And what did that huge data set show?
It revealed really clear streaming motions, patterns where stars are moving together, not just orbiting smoothly, but showing deviations in all three velocity components, radial, rotational, and even up and down.
So not a smooth flow at all.
Definitely not. They found these striking ridge-like features when you plot velocity against distance, and lots of substructure in the velocity of stars right here in our solar neighborhood, like the well-known Hercules stream.
And the sources say this complex, almost messy local picture really didn't fit well with the simple idea of a settled, well-mixed disk that the steady-state density wave theory often assumes.
That's right. The local dynamics looked complicated. However, and this is where it gets confusing, another study around the same time by Eulers and colleagues actually did manage to fit a steady-state spiral model to the same DR2 data. They even estimated things like the arm strength and pitch angle.
Wait, so the same data supported conflicting interpretations?
Kinda, yeah. It just shows how complex the data is and how much the analysis method matters. It highlights the challenge. The signals might be subtle or degenerate.
Okay, moving on. EDR3 Enhanced Data Release 3. What did that add?
Further improvements in accuracy. Studies using EDR3 looked at open star clusters, for example, to trace the arms and try to measure the pattern speed, how fast the spiral pattern itself rotates, if it is a pattern. They found some evidence that this pattern speed might actually decrease as you go further out from the galactic center. Other work combined EDR3 with infrared data on red clump stars to trace the shape of the outer arm more continuously, and even found a kind of wave-like asymmetry, a warp, above and below the galactic plane linked to the arms.
More detail, more structure. And then the latest big one, DR3.
DR3 was another major leap. Over 33 million stars with full 6D data, plus physical parameters for hundreds of millions more. Scientists like Dremel and colleagues use specific tracers, very young hot OB stars in young clusters, great for outlining where stars just formed, so presumably along the arms.
What did those young tracers show?
They mapped things like our local arm, the Orion Spur, showing it's pretty long, at least 8 kiloparsecs. They also saw features in the outer disk that lined up with arms seen in gas surveys, maybe extensions of arms like Perseus.
Okay. And they also used older stars, right? Red giants.
Yeah, millions of red giant branch stars. These are older, so they trace the underlying mass distribution and velocity field more broadly. With these, they could clearly see the kinematic signature of the central bar, how its gravity pulls stars into non-circular orbits. And they saw streaming motions out on the disk, too.
But were those outer disk motions clearly tied to the spiral arms this time?
This is the key point from the sources. The Dremel study concluded that the evidence for streaming specifically caused by spiral arms in those older red giants was actually much less compelling than the streaming caused by the bar.
So the bar's influence might be dominating the motions they saw.
It seems so, at least for that older population. They said if there are arm-related streaming motions present, they'd be more consistent with the two-armed structure often seen in infrared light, which also traces older stars, rather than a four-armed pattern.
That's really interesting. Gaia is showing us the motions, but pinning down the cause, arms, bar, something else is still tough. Let's quickly revisit the Sagittarius dwarf idea. Did Gaia data shed light on that?
Yes, a study by Antoja and team used DR2 data and specifically modeled what a past interaction with the Sagittarius dwarf would do to stellar motions in the Milky Way disk.
And did the model match the observations?
Remarkably well, according to their paper. They found that the complex patterns seen in the DR2 velocities, those ridges and streams, showed a strong similarity to what their simulation of a tidal encounter predicted.
So, supporting the idea that Sagittarius gave the disk a kick?
It suggests that such an encounter could generate the kinds of velocity wiggles we see, and that these perturbations might then wind up over a billion years or two into a spiral structure, perhaps a two-armed one. So it adds weight to the external trigger hypothesis.
Okay, so we have evidence pointing towards internal generation, maybe stable waves, maybe transient features, the bar playing a big role, and external interactions. Where does this leave the consensus view, according to the sources like that Selwood and Masters review?
Well, that review argues that because we see spiral arms and so many disk galaxies out there, the most likely general explanation is probably something internal, those self-excited instabilities, like groove modes, perhaps.
They think internal mechanisms are the default.
That seems to be their stance. They argue that while things like bars and tidal encounters definitely can create spiral arms in specific galaxies, they probably don't explain the sheer ubiquity of spirals across the universe.
But they also added a major caveat, didn't they?
Yes. Crucially, they point out that even though these internal instability models work nicely in simulations, we still lack definitive direct observational proof that these specific mechanisms are actually what's happening in real galaxies, including our own. We haven't clearly seen the groove mode cycle in action, for instance.
So the theory is plausible, maybe even likely, but the smoking gun observation is still missing.
Pretty much. The hope is that maybe future Gaia data releases or other upcoming surveys might finally give us that clear signature.
It really paints a picture of, well, ongoing research. We have these powerful internal theories. We have Gaia showing incredible kinematic detail, evidence for the bar's strong influence, hints of external nudges. But putting it all together into one coherent story for the Milky Way's arms is still proving incredibly difficult.
Exactly. It's kind of ironic, as the sources mentioned. We can study our own galaxy in more detail than any other, yet its structure, especially the arms, remains surprisingly fuzzy and debated compared to the seemingly clearer pictures we get of distant galaxies, albeit with much less resolution.
So just to recap, we started with a basic barred spiral structure, the challenge of being inside it, looked at the different mapping techniques, the competing origin theories, internal generation, like groove modes, steady density waves, external kicks from Sagittarius.
And then we saw how Gaia, through DR1, BR2, EDR3, and DR3, had just flooded the field with data, revealing complex streaming motions, ridges, warps, maybe transient arms, the strong influence of the bar, and evidence consistent with tidal interactions.
It's undeniable progress. The level of detail we have now about how stars are moving in our galaxy is just staggering compared to a decade ago.
Absolutely. But the fundamental why and how for our own spiral arms, their precise nature, their dominant origin, their evolution, those big questions are still very much driving active research.
It really leaves you with a final thought, doesn't it? We're pouring immense resources and brain power into just mapping and understanding the arms of our galaxy, the one right here. Given how complex and uncertain it still is, even with all this data, what does that tell us about our understanding of those beautiful spiral galaxies we see millions or billions of light years away? How confident can we really be about interpreting their structures based on comparatively blurry images and much less kinematic data?
It's a humbling perspective for sure. It just highlights how much more there is to learn, even about our own cosmic neighborhood.
Definitely something to think about next time you look up. Thanks for joining us for this deep dive.